Today we're doing the same thing we did last time. Well, last time we talked about optimization problems, and we're basically doing the exact same type of problem, just more examples. That's all we'll do. So let's see here. I don't like that one. Did we do the one with the cylinder? We did the one with the cone. That's all we did? All right, today we're going to do this one. So this is a classic problem. Here it is. You're making cans, like Campbell's soup cans of some sort. You're making cans. There we go. Can. This is H here, and there's R. Now, when you do these problems, you either need to tell me what your variables are or draw your picture to the point to make your picture detailed enough that it's obvious. Does that make sense? If you just throw letters at me, then I have no idea what's going on. Even I can't figure that out. All right, so you're making cans. Here they are. And the top and bottom are made out of a material that's twice as expensive. That's twice as expensive. So 2 times more expensive than the material you use for this side, than the lateral material. All right. Find the ratio. Find the ratio of the height to the base. That minimizes the cost for a given volume. So I say I want to hold, 10 liters. Then you're going to tell me a ratio of the height to the base. The base, here's the base right there. Height to the base. Base radius. Height to the radius. That minimizes cost. That's the problem. Does that make sense? All right. So the first thing we need is a formula for the volume of the can. What's the formula for the volume of a can? Now, you guys should all know this because this isn't hard. Cone's a little bit harder, the sphere's a little bit harder, but this one's not hard. How do we do this one? Yeah, first we find the area of this piece, and then we imagine multiplying it by h. That's good? Okay. So the volume, that's not how you make a V. Volume equals pi r squared times h. Pi r squared times h. Now, what do we want to minimize here? We want to minimize the cost, right? Which is related to surface area. Right, right. And so the volume, we know this is true. And what is the cost? The cost is going to be something like, well, we'll have the area of the top, so that's going to be pi r squared, right? Pi r squared. And I'm leaving some space on either side intentionally, all right, because I'm going to put something there. Pi r squared. And how many of them, how many of the top, we have two of them, right? But they're twice as much. They cost twice as much, right? So I'm going to put a 4 right here. It's 2 times because they cost twice as much, and there's 2 of them. 2 times 2 is 4. The cost plus, and now we need to know this lateral area, because that's going to cost a certain amount, right? And we could even, if we wanted to, we could even put a variable here, but this will cancel out, like times like the cost of. Here, I'm sorry. Just don't change anything on your paper because nothing's going to change. 2 for the top and the bottom times 2 times the cost. It's the same. I'm just trying to explain it better. I'm probably explaining it worse. The more, whatever. Okay, so now, plus the surface area of the lateral side, right? And so that's going to be, that's going to be the circumference of a circle, right? Times the height. That's how I'm thinking about it. So the circumference of a circle is 2 pi r times height. And then if we want to put times whatever it cost. Here's our cost. These c's will cancel at the end of the day. If you didn't put them in, I don't think I would fret. But I'm putting them in just for being complete. Because when you take the ratio at the end of the day, those will cancel. Now, what do we want to minimize here? We want to minimize, he says radius, and that's a good idea, right? But we want to minimize cost. We want to minimize cost. Since we want to minimize cost, what we're going to do is we're going to say, hey, can I take the derivative of one of these things? And he says we want to minimize radius. Now, look, we have this relationship here between the radius and the height, right? So what we'll do is we'll solve for the radius. We'll solve for the height. That'll be easiest. And then plug it back in and then minimize the radius. Does that make sense? That sounds good to me. So if I solve for height here, what do I have? I have volume over pi r squared is equal to h. That came from this formula right here. And now I'll plug this in for h over here and see what happens. All right, so cost is equal to 4 pi r squared times whatever the lowercase c is. That's the base cost of our lateral side. Times 2 pi r times v over pi r squared. This is h times c. Is that acceptable? Acceptable is good enough. All right, so now I'm going to cancel some stuff because I can't help myself. So I'll cancel those pi's. Cancel those pi's. And I really want to cancel one of these r's. So here I'll cancel. So now this becomes a 1. And I'll rewrite it. Cost is equal to 4 pi r squared times c plus 2v all over r times c. Now I want to minimize costs. And how do you minimize something? What's the calculus-y way to do it? What? Cancel it out. Take the derivative. Take the derivative and set the derivative equal to 0 and find out which radius gives us a derivative of 0. Now, the volume here, is the volume changing, by the way? No, the company said we want, some volume. And is it easy to take the derivative of constants that you don't know? What's the derivative of any constant? It's 0. So you're not afraid of these unknowns here. So cos prime is equal to, all right, this is a constant, 4 pi times c times 2r. There we go. That's that first term. Now let's take the derivative of the second one. This one's a little harder, but it's not too bad still. So it's going to be 2 times v times c. And now I have the derivative of 1 over r that I have to put here. Yeah, what's up? This is a c. It's there. Is that better? Sorry. That's a c. So how do we, what's the derivative of 1 over r with respect to r? Oh, that's a good guess, right? Well, it might be. I don't know. Let's see. Let me be a little slower, okay? That doesn't sound right to me, but let's see. 1 over r is equal to r to the minus 1. So d over dr of r to the minus 1 is equal to minus 1 times r to the minus 2, right? So this is equal to minus 1. This is equal to minus 1 over r squared. Is that right? Yeah. So that goes here. So this is minus 1 over r squared. And we want to minimize this. Maximize or minimize. We want to minimize. You usually want to minimize the cost if you're selling something, I guess. So we want to minimize this. So set this equal to 0. Set this equal to 0. And so I'm going to get, let's see, 0 is equal to 4 pi times c times, 4 times 2 is 8. So it's going to be 8 pi times c times r plus 2 times v times c minus, let's put a minus there, minus 2 times v times c over r squared. Over r squared. Blah. It doesn't matter. He says, is it just c over r squared? It doesn't matter. 2 times v times c over r squared is equal to 2 times v times c over r squared. They are the same. You only have problems if you're adding or subtracting. That's when you have trouble. All right, so I want to set this thing equal to 0. How the heck do I do that? What do I do next? What? I did set it to 0. Yep. Now what do I do? Yeah. Set it equal to c. What else could I? Why am I'm pausing. Yeah. Yeah, why am I pausing here? I mean, I kind of, when I know what to do, I just kind of keep on going. But now I'm pausing for just a second. Does anybody? I have lots of variables, but that doesn't scare me. I'm scared of a lot of things, the dark. But these don't scare me because this is a constant, and I'm cool with that. And this is also a constant, I'm cool with that. This is a constant, I'm cool with that. What's the problem? Why am I not just solving this? What do I have to do to solve it? What's the first step? You guys have given me lots of steps. They're not, I know I'm asking you to read my mind, but what would be a good common factor to divide out by? How about okay, fine, we can do that. We can divide out by 2. So this is equal to 4. We can divide out by c, right? Times r minus 2v over r squared. Now what do I do? Well, it's this 2 goes to, sorry. Now what do I do? These are good stuff, but these aren't what was freaking me out. I got this r squared on the bottom. What am I supposed to do with that r squared on the bottom? That's what I'm supposed to solve for. And the r squared is in the denominator. How do I handle it? This isn't tough. I can just multiply everything by r squared at this point. Multiply everything by r squared. Is r is not equal to 0, right? No, there's no way that r is equal to 0. We have a tin can, it has some positive volume. R cannot be 0. So r is not equal to 0. So multiply both sides by r squared. And I'm going to get 0 is equal to 4 pi r cubed minus v. There we go. Put v on the other side, and I get v is equal to 4 pi r cubed, don't I? Now I can divide both sides by 4 pi, and I get v over 4 pi is equal to r cubed. And I can solve this. This I can solve. I take the cube root of both sides, and I get the cube root of v over 4 pi is equal to r. Awesome. Okay, so I'm done, right? Am I done? I better check to make sure this is a minimum. Also, the question was asking me for a ratio, so I better deliver that ratio rather than just stopping with this part. I mean, I kind of did a lot of the work, but I better check. So how do I check to see if this is actually a minimum or a maximum? How could you check? I walk up to you in the middle of the street, and I say, hey, check this as easily as possible. How could you check? Plug in a graphing calculator to look at the graph. That's an outstanding way to do it. Probably on a test, we're going to ask you to show some work, okay? But this is a good way for you to check yourself and say, yep, I'm doing the right thing. Relax. Just keep on working, right? Okay, so what's a more computational way to check? What do? I take the second derivative, right? And taking the second derivative is not so bad. Let's go ahead and do it. I have to compute cost prime. Now let's see. What equations do I need to make sure I don't erase? Well, I have to remember that v over pi r squared is equal to h, because I have to retrieve h at the end of the day to get my ratio, don't I? So I'll keep that, and I'll keep this question. So I'm going to erase this part. Erasing now. All right. So take the second derivative. Oh, goodness. All right. So cost double prime. Let's do it. Cost double prime is equal to, oh, that's easy. 4 pi, it's equal to 8 pi c. 8 pi c, that's this term, right? Because I'm taking the derivative with respect to r, right? I'm taking the derivative with respect to r. That means that r is the variable. And now I'm going to take the derivative of this. And remember, last time I kind of, oh, I think I'm super good at this now. Okay, so now this is going to be plus 2 VC times, that's r, that's minus r to the minus 2. When I take the derivative, the minus 2 is going to come down, giving us a positive 2. Positive 2 over r cubed. Right? I think that's right. Aha! So now I get cost double prime is equal to 8 pi c plus 4, oh geez, vc over 1 over r cubed. Okay, I just took the second derivative. What the heck am I supposed to do now? How is this supposed to help us? That's right. You plug in our r, right? You plug in our r, and I'm going to get, well, plug in our r, and we're going to get 8 pi c plus 4 vc times 1 over, oh geez, 4, no, v over 4 pi. Okay, now let's start to relax. I can do this. So these will cancel, and the 4s will cancel, and that's 1 over pi. So it's 8 pi c plus 4c times pi. Whew. Oh, the 4's canceled. Stupid part. All right. And is this number positive or negative? I think it's 1 over pi, which is equal to pi. So, is this number positive or negative? It's positive. If it's positive, that means the curve is concave. Yo. The 4's don't cancel, Bart. That's 16. Thank you. Thank you. The 4's don't cancel. All right, is this positive or negative? It's positive. That means the curve is concave. Up, that means that we have a minimum. Fantastic. It's a lot of work, but optimization problems shouldn't really scare you too much, okay? Because, yeah, it's a lot of work, but, okay, let's finish it before I start patting ourselves on the back for doing it. Okay, so this is a local minimum. This is a minimum for this. Great. We got to find h, so if r equals this, then h is equal to v over pi r squared. So v over pi, oh geez, cube root of v over 4 pi squared. And then for some reason, the question asked for the ratio of these things. Oh, it asked for the ratio of base to height, the height to the base. So let's put the height over the base. So that's going to be the height is v over pi something squared, a cube root, v over 4 pi. Oh, this is ugly. All over this cube root of v over 4 pi. Where did I leave this? Ooh. Isn't one of these things... No! Volume pi r squared times h. Why do I have pi r cubed times h? We should be able to simplify this a bit. I don't see myself doing a very good job at it, though. Yes, please ask. she says, why am I using the radius as the base? Don't I need to double it? You're right, but she's right, but this should just say radius of the base. I'm unfortunately not making a mistake here, right? I'm sorry. That was my fault. Okay. Yeah, but I am doing something silly, and I'm trying to figure out. Yeah. Oh, I know what I'm doing silly. This is right, all right? I can simplify this if you want me to, but I have to go back a step. I'd rather not, because it's not important to our class. Here's the sneaky way to do this. What you do is you say, you do this a little sneaky. You say h over r is equal to h over r. Yeah. H. So we know this, and so what you do is you say h over r. From here, just get h over r. This is now pi r cubed over h over r. Look at this. What did I do? I just divided both sides by r. Super sneaky. Maybe not super sneaky, but sneakier than me. Okay, so, and now if you plug our h over r there, if you plug in our r here, and you cube it, it becomes nicer. What's up? What do you want me to do? Yep. So this is right here. And so this is equal to v over pi. Yeah, that works. I don't know why I was so scared. There we go. 4 pi cubed. Right? Okay, and now, okay, yeah. This is nice now. Okay, so this is equal to, I don't know why I was freaking out so much. I'm sorry, folks. Okay, v over 4 pi, right? Now the pi's cancel. This is equal to, this is just equal to 4 then. No stupid trick needed. But do you need to simplify your answer? No. Okay. Whew. It's 4. She says, what's the final answer, right? The final answer, because this was asking for this ratio, you could leave it here. This is fine. We simplified it down a little bit here. We simplified it again, and we got 4.
So from that h to that h,
Every h is the same. Why she says they don't look the same, Bart. It's because what's r equal to? We plugged in that thing for r squared. That's why they don't look the same. So here's what I want you to do. I want you to tell me, I think what would be good now is let's talk about how to solve an optimization problem. What do you need to show? And then we'll do one more, and we'll see. We'll do some more then. So how do you solve an optimization problem? What's the first step to solving an optimization problem? You should draw a picture. Can I erase this? Is that okay? I have not seen your exam. I have no idea what could be on it. But I would guess there's going to be one optimization problem on it. Why? Because we've done all this curve sketching stuff. We've done all this max-min stuff. We've done all this. It has you take a derivative. I can't. There has to be an optimization problem on your exam. It has to be there. And let's see. So what do you need to do? Step 1, draw a picture. Put all your variables on it. Put as many variables as possible. Well, okay, you guys know what I mean? Like, don't just like put letters all over the place. Okay, as needed. Label things. Two, what's the second step? What did we do here? We found an equation. Find an equation. Find an equation with, usually with one variable. And why do I only want one? You can have other constants around. That's not a big deal. But only one variable. Why do I want only one variable? Two variables. Well, we want to take the derivative next, right? And you got to know what to take the derivative with respect to. By the way, there are times that we combine related rates questions with optimization questions. That's like the hardest one. Okay, so find an equation with one variable. What's the next step? Take the derivative. With respect to that one variable. Okay, and then what do? We just took the derivative, set it equal to 0. Set derivative equal to 0. And then what do? Solve, right? Solve for a variable. Take the second derivative. Actually, if you have time, you should always plot and see what happens. Does anybody know why? Because it will guide your next step. What if the second, it will probably almost never happen that the second derivative is 0. But if it would happen that way, then you would know what to do next. If you look at the plot and you say, oh my God, the second derivative is 0 at my point, you don't know anything. It has to be positive to be concave up, negative to be concave down. If you have the plot around, you say, no problem, no problem. I just plug in 2 points on either side, and I say, see, they're above it, and then I try to make some argument that there can't be any other zeros or something like this. You know, does that make any sense? No? That's okay. Okay, so what I'm saying is, if you have time, and if you're skilled with the calculator, you should check and look at the plot and just double check your work at that point. Make sure that it makes sense. What if you aren't at a maximum or a minimum? That means you go back and you take the derivative again and you solve again, right? That's what it should mean that you do. Before you take the second derivative, because it can kind of guide what you should do. Maybe you should plot here, right? And if you plot here, it will tell you the answer it'll tell you close to what this answer should be. Yeah, what's up? She says, Bart, you're talking about plotting, and what are you plotting? You plot the derivative. If you plot the derivative, because you're going to be solving for where the derivative equals 0, right? So if you plot that, it will help. Now, this isn't your answer, but I'm trying to help you guys What does everybody hate to do on a math test? Fail, yep, we all hate to fail. I hate to fail. Yeah, hate to fail. We hate making stupid mistakes, right? You hate being counted off for something that really isn't a big mistake. So this is a way for you to check your work as you're going along. Take the second, okay. So that's my little spiel. So you could check here. Check here to help with that. Take second derivative. Plug in the thing you found here. Wow, this is hard stuff. You know, kind of just keeping track of everything you have to do. Plug in the root you just found. Check concavity. If it's positive, it's concave. Up. Positive. Up. Concave up. The cave side's on the up. So therefore you have a minimum. Make sure you have a minimum. Make sure. Ugh. It'd be awesome if I could do the splits, you know? It'd be awesome if I could do the splits and moonwalk. Because if I can moonwalk, then I could like right backward or whatever. Same, make sure you have a max or min. Okay. Whew. And then finally, make sure you answer the question. Because God knows what happened between here and the, right? Ugh. Okay. Are we ready to do another problem? You're like, here we go. I like this problem, but it's hard. At least I think it's hard. Maybe it's not that hard. I hope it's not that hard. How many more weeks do we have left of school? 6? I thought we only had 5. What? Oh, yeah, I don't count exams. I don't take those. So, right, 6, yeah. Woo! God, we have half a quarter left. Okay, so this is also sort of a standard problem. All right, here we go. This is a road. This is a bike path. You're riding a bike. You're riding a bike down a bike path. That's my bike. All right, you're going this way on the bike path. You start off at some point. Here's some other point. And this area here, that's all grass. This is all grassy stuff. And for some reason, you decide you want to bike here. All right, maybe there's a picnic table up there, and you want to have a picnic. All right, that sounds nice. And this point here makes a right angle. That's a right triangle right there. Now, actually, the story is actually better if that's a porta potty. You're riding your bike and you have to go to the bathroom. So now you got to get to the porta potty as fast as possible. Okay. So, fine, it's a picnic table. But anyways, the question is, where do you turn off? If you're going to make a straight line, where do you turn off the bike path? Because you go faster on the bike path, and when you get on the grass, you start going slower. I mean, it's bumpy, right? So you want to somehow maximize this, okay? And so this will be point A. Oh, goodness. And this is going to be point B here. That's not point B. Oh, goodness gracious, Bart. Here, the point where you turn is point B. This point down here is point C, and this is point D. And so presumably, you're going to make a route like so. So from here to here, and then you're going to go up like this. This is the problem. Now, sorry that I'm telling you the problem rather than writing it down, but does it make sense? I think it should make sense, right? And so the question is, where is this point B? All right, so here's what you know. You know a couple things. This is all done very, very generally. That distance is A, right there. This distance here, is B. All right. How fast are you going? You're going a certain speed. Now, your bike goes a certain speed on the sidewalk. That's V. And it goes a slower speed on the grass. W. So these are speeds. These are speeds here. That's speed. Now this, there's x. And so here, this is finally, we got it. So we're driving along. We're riding along at speed v. We're going to turn our bike off, go onto the grass, slow down presumably to speed w, and get to a. And we want to know, how do we minimize the time, right? I think that's the only way to put it. Sound good? Does this problem seem hard? I don't know. Yeah. We do but we do it exactly the same way. We do it exactly the same way. How do we? Oh, we draw a picture. Picture drawing. Put as many variables as needed. Okay, we did that too. Now, what are v and w again? They're speeds. They're speeds. They're constants too, but they're also speeds. Okay. The only thing that's really changing here is x is changing, and this distance here can change. That's the only thing that can change in this problem. Okay, great. So now we just find an equation with one variable, right? What's the distance from B to A, by the way? What's this distance? What's this distance right here? If this is lowercase b, square root of x squared plus b squared. Okay, great. So now, we want to minimize time. Right? So we should write a formula of time in it. So time of x, this is time of x, is equal to, so let's see, we can write this as down, I think. Time of x is equal to, well, what? Yeah! Okay, so distance equals rate times time. Why don't you write it correctly, Bart? And then so time is equal to distance over rate, correct? Aha! Okay, so I know my rates. There's my v rate plus there's my w rate, right? And then here, this is the square root of x squared plus b squared, and this one here is a minus x. Why didn't I make this one x? If this, so this is a minus x here, right? Why didn't I make this one x and this one a minus x? Any thoughts on that? Was I being? I think I was being smart. I wanted to be able to use the x here because this is a much nastier expression. So I wanted to be able to use the x there. All right. So there's our formula. That's awesome. Okay. Great. Everything else is a constant. What do we do now? Take the derivative. We just take the derivative, and we're strong and tough at taking derivatives. So t, yeah, let's do it. How about we simplify this a little bit? This is equal to, there's not much simplifying to do, I guess. T prime of x is equal to, what's the derivative of the top with respect to x? A minus 1 over v. Oh, did I make a mistake? A is a constant. A is the distance. Lowercase a is this distance right here. You're moving, but the distance between this point and this point isn't changing. It's not the distance between you, it's the distance between this point right here. Okay, so that's the derivative of the first term. How about the second one? Oh my goodness. Well, that's not so bad. Plus, how do I take the derivative of the square root? I think of it as to the 1/2, right? Oh yeah, this is how I do it. I do it like this. I say, this is w, I put a half here, I make this x squared plus b squared, and I do 1/2 minus 1, which is minus 1/2. And then what do I do? Derivative of the inside, I have to do the chain rule times 2x. There it is. And now we are going to simplify this. Talk. Why does the b go away but the x doesn't? Oh, this a right here. Yeah, that should go away. Thank you. That goes away. All right, let's simplify this. T prime of x is equal to minus 1 over b plus, let's see. Oh, what happens to the 1/2 and the 2? Cancel, right? And it's going to be x over w square root of x squared plus b squared. Is that correct? Oh, because it's to the minus 1/2 power, right? Minus 1/2. The minus throws you downstairs. The 1/2 is the square root. He said, why is that one? Whatever. Okay, so now we got this. What do we do now? Set it equal to 0. Fantastic. 0 is equal to minus 1 over v plus x over w square root of x squared plus b squared. Did I do this problem already in this class? I just had like deja vu. All right, so now I want to solve for x. Hey, this isn't so bad. What I'm going to do is I'm going to add 1 over v, minus 1 over v to both sides. Add minus 1 over v, so I get 1 over v is equal to x over w, square root of x squared plus v squared. And we have like 3 more minutes or something like that. Let's go ahead and just solve for x if I can. How do I solve for x? I can multiply both sides by w, right? W over v equals x over square root of x squared plus b squared. What do I do now? This means square both sides. I know how you're supposed to know that. Okay, but square both sides. W squared over V squared is equal to X squared over X squared plus B squared. Oh man, this is so hard. Can you guys solve for X from here or not? I don't know. What do? You multiply both sides by this. So I get X squared plus B squared times W squared over V squared equals X squared. You got to distribute. Oh no. X squared W squared over V squared plus B squared W squared over V squared equals X squared. Now I subtract. And I'm going to get, let's see, X squared times 1 minus W squared over V squared equals W squared over V squared. Throw it on the other side, so I get W squared over V squared times 1 minus W squared of V squared, like so. Write it correctly, Bart. W squared all over V squared 1 minus W squared over V squared equals X squared. And then what do? Take the square root. That would be your candidate for the 0. You plug it into the second derivative. It's a little bit of work. All right? We'll end here for today.